So for my half a dozen or so YouTube followers, my internet has been fixed. Hooray! I actually did get an email from someone. They were like, "Did you cancel class today?" I'm like, "No, my video didn't work, but it's working again." I have emerged victorious over my laptop. Now we'll see how long it takes for Windows to restart itself, for Office to update itself without my permission, but you know, you got to fight one battle at a time. So I have adjusted the due date for homework 4, which is now officially ready for you to begin. I've moved it to the following Monday. So it was going to be due on the 2nd. I moved it to the 5th. I still don't know for sure if I'm going to be here on the 5th. That's my jury duty day. So if they decide they don't like me, it's possible they'll dismiss me in the morning and I'll be here in the afternoon. If not, if I have to stay, then I was going to ask Jihong to come in my stead and not teach anything new, but just have the lab open so that you can work on the assignment and answer any last-minute questions. As of right now, there are 4 sections to homework 4. You can do 3 out of the 4. The 4th is the material from today and that possibly will stretch into next week. It's the same idea as homework 2. It's literally the same data, the same 24 items measuring gambling. It's going to give you a chance to get used to fitting models for binary data in M+, using ML and using WLSMV, trying to figure out what the parameters mean, where to find them, that kind of stuff, and then doing the same thing with polynomous models, as they are called, for Likert scale type data. So in homework 4, I made your data set for you. I made you a starter syntax file. So the hope is that you can just use that and use the templates from class to get going immediately rather than fighting with software and outporting, is that a word? Exporting, outputting data. So let me know if you have any questions with that. Jihong has office hours tomorrow as well from 1 to 4, so on every Thursday, so you should have plenty of chances to get questions answered, and of course you can ask them during class. Let's see. So yeah, we're ready to start a new section, although it's not going to be all that new. It's just going to be a slightly more extended twist on what we already know for binary. So we'll still have our friends logit and probit. That's going to take our bounded outcome, in this case Likert type responses, ordinal responses or nominal, and it's going to transform the to-be-predicted outcome into something that's continuous and symmetric about 0. Both logits and probits do that. So in the interest of time, I have decided to omit certain things from this section of Lecture 6 and put the handouts up online. I will try to get the videos that I did last time to go with it, but we're not going to have time to cover basically the last 2 options in here, but I have a handout that goes over those. So rather than review generalized models just on their own, I'd like to just jump into the latent trait version because I think you guys are ready for that given how much time we spent on binary. And so we'll focus then on 3 different kinds of models that you can fit to Likert type data. So basically anytime you have numbers that don't necessarily represent numbers, they represent choices. So it's categorical data like 1, 2, 3 or 1, 2, 3, 4, 1, 2, 3, 4, 5. In M+, you can go up to 10 with this type of data. So it's either ordered, which is usually the case when you have Likert type responses. Maybe it's ordered, but you're not entirely sure, or it's not ordered at all. And there is a specific type of model that goes with each of those types of data. The new handout that Jihong and I are working on that he's going to present is going to focus on these last 2. The example that I have to do today is going to cover the first one. So we, at the end of class last time, since we built this little spreadsheet, the idea that even if you have non-binary data, it's still going to be a series of binary models. And so these 3 differ in how they divide up the models. So I'm going to switch this phrase here to be graded response because that's what it's called in the world of IRT. So let's say that we have a 5-category outcome variable. How many of you have items with 5 categories? Lots of people. 4 categories? Yeah? Okay, so for you, just pretend there's no 5. It works the same way. So you will have number of categories minus 1 binary submodels that you're going to be working with here. So the conditional distribution for all of these things is going to be multinomial. It's basically the same as Bernoulli, except there's a separate p for every possible category minus 1, because the last one is determined as 1 minus the sum of those. But the models differ in how they create these binary submodels for analysis. So the one that is used, I would say, by far the most often is this one that's known as graded response. And this formulation takes each submodel, divides it up into something binary, but uses all the data each time. So the first submodel would model the probability of something greater than 1. So it cuts the total that we would refer to, let me put a new line in here just to make this a little bit easier to understand. So graded response can also be written this way, and I wrote it this way last time. It's 1 versus 2, 3, 4, 5. Next one is 1, 2 versus 3, 4, 5. 1, 2, 3 versus 4, 5. 1, 2, 3, 4 versus 5. So it lumps all the ones that I've written together into one column. So it's like it's recoding the data. So each time it uses all the data, but it focuses on a different transition point. And what you're going to get out of this model is the theta value at which switching to the other option happens with 50% probability. So because there's 4 submodels, there's going to be 4 difficulty values. Alternatively, there's 4 thresholds. And the same mathematics to get from one to the other holds in these cases as well. The catch is that because all 4 of these describe one item, you only get one loading. It's the same loading shared across all 4 submodels. So the effect on the logit of a 1-unit increase in your trait doesn't care which logit it is. It's the same effect of an increase in theta, whether you're talking about switching from 1 to greater than 1, 2 to greater than 2, 3 to greater than 3, and so forth. So let's take a look at what this is going to look like. So I'm going to pick up on right here. So this is slide 8. Skipping ahead a little bit, but this is the beginning of where the latent trait stuff. So this is what's known as a graded response model. I want to say the reference to this is Samajima 1969, I want to say, or thereabouts. So don't get confused thinking that this is new and modern. It's not. It's old, but it's just not as common. So this is what's known as a graded response model. In the world of non-latent trait models, this is also known as a proportional odds model, or a multinomial or ordinal regression, depending on your software package. In Stata, it's O-logit, for instance. This model is commonly used for Likert-type data. This is the case where theta is just an unobserved predictor. So for instance, if I have 4 categories, I have 3 submodels. And the location parameter, the threshold, intercept, or difficulty, in M+, they use dollar signs to indicate these. So do you remember we had $1 for the threshold before in binary? Now, because we're going to have as many thresholds as we have binary submodels, the thresholds get numbered. So 1 is the first one, 2 is the second, and 3 is the third. The catch is that you have to know your data to know what that means. So let's say, for instance, in this setup right here, where there's 5 options and 4 submodels, you have, let's say, 100 answers here, 50 answers here, 25 answers here, and no answers here. Could that happen? Sure. Actually, let me make 100 here, 100 there, 100 of 1, 100 of 2, and so forth. So this would be category 1, submodel 1. This would be 2, this would be 3, and you wouldn't have a 4. Now what if instead it went like this. They skipped the fourth option. Nobody answered 4, but a bunch of people answered 5. Less common, but can happen. M plus will still call the first transition 1. This is still 2. And then this is 3. So you have to know which categories were actually answered, if you're missing some, to know what those $ threshold indicators mean. So if you don't have as many thresholds as you think you should, go back and check your data, because you need to make sure which category wasn't answered, you know for sure. That gets spit out at the beginning of the output, by the way, so you can check that yourself. One nice feature, hey, don't start updating, I'm going to lose my mind. There you go. So you listened. One nice feature of this particular model is that the number of response options doesn't have to be the same. You can fit this model to items that have 2 categories, items that have 3 categories, 4, 5. So more generally, because of missing data or because of design, they don't have to be the same. Each model, each item rather, gets its own set of submodels. There's no inference that category 3, for instance here, the third transition, is the same across items. And so we'll see evidence of how that plays out in real data. So as we saw with binary data, what M plus estimates directly are loadings and thresholds. You can then convert those into discriminations and difficulties. Unfortunately, M plus won't do it for you. But I added some extra code to my example this year. That way you can get M plus to do it if you know how to ask. And of course, for whatever reason, certain equations always end up moving themselves back to the middle of my screen. I have fixed this once a year or more every single time I've taught this course. And it never, ever listens to me. There. As I were. Come back. There we go. There. So here's what a model would look like for a 4-category variable. The top section is written as the IRT version with A's and B's. So let's look at that first. So if I have responses of 0, 1, 2, or 3, then the first submodel is going to describe the logit of 0 versus 1, where 1 means that they got a 1, a 2, or a 3. The second submodel describes the logit of 0 versus 1, in which 0 is either 0 or 1, and the 1 is the 2 or the 3. So it's binary in the sense that you can still think of it as 0 or 1, but I think it's less confusing to just think of it as the lower or the higher. Because each time it's what 0 and 1 means switches, depending on which submodel you're talking about. So note in the notation here, the logit that y is greater than 0, so the green part here is A, where A is sub I. That means it's the same A across all three submodels. Here's our friend theta. What's theta again? You know this one. This is a softball. Slow pitch softball. What's theta? There's almost as many synonyms as there are people here. I could go around and ask one for each of you. Latent trait, factor, latent construct, true score, take your pick, right? That's what theta is. Theta gets an S subscript because it's a subject thing, not an item thing. So we're assuming that the same theta is responsible for item responses. B then gets an I subscript and a number. The I refers to which item it's for. The number refers to which binary submodel. So note that I've got a B1, a B2, and a B3. So B1 is the theta at which an answer of greater than 0 is 50-50. B2 is the theta at which an answer greater than 1 is 50-50. The probability is, that's what I'm referring to. The logit is 0, the probability is 50-50. And last but not least, B3 is the theta value at which the probability of 3 instead of something below 3 is 50-50. So these models are tied to that reference point of 50-50 or logit 0 as the interpretation of B. That's the version that I still think is more intuitive. And I'll show you examples of some reports that I've made folks in estimating these models for people who don't necessarily understand IRT. The analog to this then, this is the IFA model, where we are instead using a threshold and a loading. So what the threshold conveys directly is the logit of the red part when theta is 0, when factor is 0, take your pick. An intercept would convey the logit of the green part when factor is 0. Because the model is trying to predict the green, that's why we end up with the negative sign in front. So you could write this equivalently as either intercept plus loading times factor or negative threshold plus loading times factor. M plus uses thresholds, and so that's why I've written it this way. Okay, question. B up above, okay, up above in the IRT model, B is always a theta level at which something is 50-50. What something is depends on which submodel. So B1 is the theta level at which a response of greater than 0 has a probability of 50%. B2 is the theta at which a response greater than 1 has a probability of 50%. Or that doesn't sound right. Sorry, math people, don't yell at me. You know what I mean, right? 0.5 probability, does that make more sense? Yeah. Somewhere there's a statistician shuddering as he listens to me describe this. I'm sorry. Logit 0, probability 50-50. B3 then is the theta at which the probability of greater than 2 is 0.5. There, that's better. Okay, is that better? So that means threshold down here then, that is the predicted logit of the red part when factor is 0 in each of these submodels. It's what M plus gives you. I find it less helpful. Now, one thing that's interesting about this particular IRT model as opposed to some of the others for categorical data, categorical, by the way, in this world is called polytomous. That's another vocabulary word. It just means some kind of discrete distribution. None of these models, except for one, directly tells you the probability of any given response category. It's what's known as an indirect model. To get to what the probability of each one is, you have to go between models. So for instance, if I look at the probability of y equals 0, well, the first submodel gives me the probability that y is greater than 0. So it's just 1 minus that. If I want to know what the probability of a 1 is, though, I have to go between the model that has 0 and 1 and the model that has 0 to figure out what the 1 is. So it's the probability of the first submodel minus the probability of the second. That gives me the 1 specifically. Likewise, to get to the 2, I have to compare the 0-1 model versus the 0-1-2 model. The only one that gives me a probability of an answer directly is the last one. The probability of a 3 is what's directly given by the third model. So that's just the third probability, and I put the minus 0 there to make that point. So what the parameters mean and how you want to think about them in terms of what is the probability of each answer at a given level of theta is not directly aligned as it is in some of the other models. So if I were to plot the model parameters for a 4-category item, they would look something like this. So let's say that the probability of y greater than 0 is given by the pink line here, Greater than 1 is yellow, and greater than 2 is this, I'm going to go with teal, aqua. Any takers? Teal? Okay, it's teal day. So the first B value then is -2. That is the theta point right here, where the transition from 0 to something greater than 0 has 50%. Likewise, the second B value is 0, because that's the theta point at which the transition from y less than 1 to y greater than 1 is 50%. And then the same thing happens here at 2 for the transition between 2 and greater than 2. The curves are parallel because all of them share the same slope. There's 1a for the whole item. So it doesn't matter if you're talking about moving from 0 to 1 or 1 to 2 or 2 to 3. The same effective theta is assumed for all of them. So here's an item with the same difficulties but a stronger slope. Weaker, stronger. Weaker, stronger. Here's what the predicted probabilities would look like then if you go between models to figure out what is the probability of a 0, specifically, what's the probability of a 1, a 2, and a 3. And you can get these sorts of plots. They're called item characteristic curves in EPSY, even though they're not the same thing as what they are for binary data. I would call them category response plots because that's really what the plot is intending to show. So the y-axis is the probability of answering in that category, where that category is given by the different colored lines. The x-axis is theta, mean 0, variance 1 as usual. So for low values of theta, the lowest answer is most likely. For next range values, then the 1 is most likely, then 2 is most likely, then 3. So this is what you want to see. This is good. Each category is most likely at some point. There's clear differentiation among them. Here's what you don't want to see. This is a bad item. This is the same difficulty values, but with a very low discrimination. Everything sort of collapses onto itself. Functionally speaking, there's nothing for the middle categories to do. The item is not very discriminating. Okay, how are we doing? Questions so far? Yes. Not necessarily. Here's where you can answer that question a little bit better. So this is an example of, I took this from a report that I generated. My husband and I do a little bit of consulting on the side, and this was working with the state of Nebraska on a new measure that they were giving, assessing schools and how well they, I can't even describe it very accurately, how well they participate in certain kinds of professional activities. So they had 6 different factors, each of which had 5 items. They had a 4-category scale, where it was never, sometime, never, seldom, sometimes, and one more, often, I think was the next one. So I made them this plot in Excel. I gave you the Excel spreadsheet by which I did this for our example, so you'll see another version of this here. And I turned it on its side so that the item locations were given on the y-axis here. So for this item right here, for instance, can you see my cursor? Let me make it bigger. Laser pointer. There we go. All the cats from my dozens of fans are going to go nuts. So this item right here, there's 4 options, so there's 3 difficulties. So the switch between something greater than never happens at a theta of -5. The switch from never basically to seldom, let me get the Never, seldom, sometimes, and often. So you can think of this as the switch from never to something greater than never happens here. The switch from seldom and never to something greater happens here. And the switch from never, seldom, or sometimes up to often happens up here. So this right here would indicate that all four of those categories are being used well. They're not on top of each other. In contrast, some of the other items, you start to see like this one right here. This one doesn't have a little blue block down here. Can you guess why? Yeah, no one said never. And the difference between seldom and sometimes is much more condensed. So for that item, those choices are less differentiable for whatever reason. So this helps to convey how the model takes these scores and allows them to differ across items. So all of these oranges right here represent conceptually the same thing. It's the point on the trait at which someone is more likely to pick often than anything else. It's the last one. But not all oftens are created equal. So the item in the middle here that's crossing, this is number 4, item 5, that often is the hardest to get to. It takes the most trait. So if you think about this in the context of, say, like a personality assessment, let's say something like depression, right? You might have an item that says, like how often do you cry? Often. How often do you think about killing yourself? Often. Those oftens are not the same, right? They're both 4s, but they're not the same. So this model places those transition points between categories onto the latent trait at the point at which the data say that it should go there. So this often takes more of a theta to get to than, say, this often does. It's easier to do this item more often than it is to do that item more often. So when you're looking at how well people are using your categories, this is what you want to pay attention to. How spread out are they? Are they on top of each other, or are they differentiated? If you see some that are like right next to each other, that suggests that people are not telling the difference. They're not helpful. This also tells you then, as a consequence, what your reliability is going to look like. So if you look at the scale of this y-axis here, this top line right here is 2. So we have items that go, item categories, that go all the way down to -5, but nothing that goes beyond like 1. So this scale measures low people. Well, there's lots of things for low people to agree to or to disagree to in terms of picking which answer suits them, but they top out at a trait level of 1. And so when you convert the item information curves to test information and convert that to reliability, so reliability is information over information plus 1, what ends up happening then for those 6 traits are the curves up here. They have adequate reliability for the most part, from a -4 standard deviations up to just past 0, and then it tanks. The reason it tanks is right here. There is nothing past often for high people to differentiate themselves. So part of the recommendation that I provided in the report is, hey, you know how to fix this? Add something past often. Almost always, more often than not, most of the time, I don't know, take your pick, right? But often is not high enough. So if they added a 5th category, that would help fill in the gaps on the top, and that would extend the range over which their test is going to be reliable. Then, well, what if they only want to keep 4? Well, if you want to keep 4, I would argue then potentially you might want to reconsider the difference between never and seldom. So I would add something to the top and think about condensing something towards the bottom if you had to have 4, but 5 seems like it would be reasonable. And then in thinking about which items are necessary, here's the combination here of item discriminations, and where the same item is shown right below it. So these two items right here, 1 and 2 on the third trait, those have relatively low discriminations. You might think, do we need those? Well, look how wide they are, though. Arguably, these are some of the best items in terms of spreading across the trait and having something for people at all different ranges to answer. If I were going to try to get rid of items, what I would look for are items that are largely redundant in the range in which they cover, or they don't cover much of a range. So like right here, here are basically 3 items that do the same thing. You may not need all 3. Now, an important caveat to this is that we have no idea what the content of this is. I'm just staring at the numbers. If you were going to decide whether or not to get rid of one of these 3, you might want to look at the content and make sure that you're covering whatever aspects you want to measure. But this is just saying, look, these kind of are doing the same thing. They're not as helpful. Then this item right here, should we get rid of this one because nobody answered never? I would hesitate to, because if someone were to answer never, that never would likely be clear down here. So if you potentially have a sample that could be even lower in this trait that you'd want to measure well, then having items that not everybody picked every category is not necessarily a problem, because it may just be that particular sample that didn't. It just means that we can't estimate where the difference between never and something greater than never would be, because we don't have an instance of never. So this was obtained by estimating the model in M+, translating the thresholds into B's, and then making pictures in Excel, because I'm not fancy. I hear R makes great pictures, but so does Excel if you know how to fight with it sufficiently. There is another version of the model that is a simplified version where these differences between categories can be constrained to be equal. You could do that in M+. I have never taken the time to try and figure out how to do so properly, so we can pretty much skip over that. So let's look at how this would work for the data that we've been playing with. Does that sound good? Why not? So we have example 6A. Nope, I already opened that. That's not what I want. So these are different versions of the same items that we looked at for binary data. Before it was, I think, can do it without help was a 0 or 1. Now here is another version of it. I think one of the versions was completed by someone else and the other was a self-report. I forget which it was, though. So here are the proportions of responses, percent of responses, in each of the 4 categories. So can't do it, big problems doing it, some problems doing it, and can do it. And if you look at this column right here, the last one, you can see most of the responses are in this column. So just based on that, I can tell you we're going to end up with some kind of ceiling effect, just like we saw in the binary data, where the model was, these items were unable to differentiate amongst type people. The rest of this, up to a point, is going to look remarkably similar to what we did for the binary items. So in this data set, I had dichotomous versions, which is the D versions, and then I had the categorical versions, which is the C versions. So we're switching to use those, but otherwise it's the same. Categorical R is the magic thing. So if it's binary, it's categorical R. If it's ordinal, it's categorical R. It figures out how many categories you have for each item, and thus how many thresholds you need. It understands that the loadings are to be constrained across submodels for the same item. So we're going back to full information maximum likelihood here. We're going back to logits because we can easily back translate into probabilities in that metric. If you want to save factor scores, I have the code here to do that, but we don't need to do that right now. Plots are always helpful. And here's the model. This part looks largely the same, except that I've added some labels to it. That way we can get M+ to do the math for us to get A's and B's out of this. So this is actually new for you guys. I've never done this for anyone else before. Don't you feel privileged? I did this. Whoever says that once you've taught a class it's prepped has never taught stats. There is no such thing, especially when every time I run this, M+ comes out with a new version, and I have to make sure that they haven't changed something, and they always do, because science is progressing. So we have our factor, I have named IADL, Instrumental Activities of Daily Living, is measured by items 1 to 7. Do I need this star right here, or is that optional? You would guess the other way. Yeah, it's not optional in this case. So if you don't put that star there, what M+ will do without you asking is restrict the first loading to 1 and estimate all the others. What I want to do instead is put my theta variance to 1. That way I know what the scale of my model is very easily. So that star at the end overrides the default to put the first loading to 1 and says estimate it instead and estimate all the other ones too. So don't forget it. So I have labeled these loading for item 1 dash loading for item 7. So this is an instance in which it is just a label. There is no constraint. There's going to be 7 loadings because I have 7 labels. Likewise, I now have 3 sets of thresholds for each item. So threshold 1 refers to the 0 versus greater than 0. Threshold 2 is, I'm going to just write that in there. Why make it hard, right? 0 versus 1, 2, 3. That's what that one means. This one means 0, 1 versus 2, 3. And this one means 0, 1, 2 versus, hey, stop that, 3. Now, what if you wrote all these out and you didn't realize that there were a few items where no one answered 3? What will M+ do to you? It will yell at you. It will say, I can't do that. So if you're feeling lazy and you don't want to turn your thresholds into B's, you don't need to type any of this. It estimates all possible thresholds by default. The only reason you need to list them is if you want to do something to them. Either label them so that you can use them in math, or constrain them across groups or time or something like that, which we'll do when we get to invariance. So that is not strictly necessary to write them all out. Last but not least, I have identified my factor here. Now this right here is not identified. I have told it to estimate the factor mean and the factor variance. I can't do that because I'm estimating all the loadings and all the thresholds. That means my model doesn't have a scale if I were to just do this part. But lo and behold, I am fixing it right away down here under model constraint. So that does the same thing as if I just said make my factor mean 0 and make this factor variance 1. It does the same thing to write the constraint down here. The reason I did it this way is so that I can then use these values, either estimated or set, in the formulas that follow. Because the translation of thresholds to B's requires the factor mean and the factor variance. So let's just look at what we get without any of this stuff. Here's my output, and that's all I get for model fit. Remember why? There's no perfect model. The perfect model is the contingency table that is 4 to the 7 number of cells. That works out to be 48,600. So all I get is my HO log likelihood. It turns it into AIC and BIC. So I can do relative fit comparisons. I can ask if this model is relatively better than, say, a two-factor model or a model with constrained loadings. But I can't say, based on this output, that my model fits in any kind of absolute sense. These chi-squares are useless unless I were to have like 16,000 people with which to have them actually work. So to illustrate a relative fit comparison, I took the loadings over here and constrained them to just be L. One loading instead. So by definition, the graded response model has separate loadings for each item, but you don't have to fit them all. This would be the most constrained version where all the items share a loading. So going back to my earlier days at KU, so I decided I was going to do IRT for my dissertation. And I met with Susan Embertson, who was on my committee, about what kind of sample size I would need to collect. And I had 38 items in the test that I was interested in. And she's like, well, how many people do you have? And I had spent the whole summer personally collecting every single person's data. And so I'm like, 155. And she laughed at me. She's like, no, you can't know. The hard part of these models is always the loadings. The thresholds are not hard because they come straight from the original data. If you know how many people answered each answer, you can compute the threshold. It's the loading that's the hard part. So she was thinking, you can't have 38 loadings with 155 people. And I'm like, well, thinking, okay, could I get 10 more people? Like, what would it take to make her stop laughing at me? And she said, well, 700 or 800 at least. Yeah. Well, that wasn't going to happen. So what I ended up doing is this model, where I constrain them all equal. Because she was not going to laugh at that, and I needed to graduate, right? But in reality, there's middle grounds, right? I could test the model where they all are different, even if it's not going to be estimated very precisely, make an admittedly data-driven guess about which items might be able to share a loading, and I could work with something sort of intermediate where I could let the loadings differ if they needed to, but make them share otherwise. Like a 1.5 PL is what I would think of that as. I made that joke during my defense, and other people laughed, so that was a good one. So in this model over here doesn't have a name. The graded response model is the one on the left. That's where every item gets a separate loading. I would call this a constrained version of a graded response model, and that's why the title of this handout right here is 2PL-ish and 1PL-ish, because those labels refer to binary data, but it's the same ideas as instantiated here. So in the same way that we tested the 1PL versus the 2PL with a log likelihood comparison, I did so here. So here's the output for the 1PL over here. So I had 28 parameters on the left and 22 on the right. Let's count them up. Where did 28 come from? I've got 7 items. Well, there's this 28 divided by 7 is 4. That's convenient. What does each item get? Start you off. Loading. And each 4 category item gets 3 thresholds. Yeah. How did I get 6 fewer on the right-hand side? I did 1 loading instead of 7. Yep. So the difference in -2 log likelihood is in your spreadsheet. I wrote it out for you here. So for 6 degrees of freedom, for the difference in how many parameters I estimated, chi-square, -2 difference in log likelihood here is 135. So yeah, we're going to interpret this model. Now, given that this is all I get, do I know if it fits? Did the test I just did tell me if it fits? No. What did it tell me, Adrian? It's better than the other one, but we don't know if it's good, right? It might just be like less crappy than the alternative, but we don't know if it's like good yet. Now, in full information maximum likelihood, there's not an easy way to get an overall index of good. Do you remember what we're going to do instead? Talked about last time? What's my cheaty way? Or at least the way that I'm doing now until something better comes along? Saturated model. How am I getting a saturated model? I thought I didn't have one. None of the data. Switching something, making a different choice. Switching estimators, yes. So this was the other thing we had talked about. I'm in full information maximum likelihood, but if I want to get some sort of easy way of judging absolute fit, I can switch estimators. So we'll do that too, to look at absolute fit. For now, let's just pretend that it does fit, so we can look at what the model is actually saying. And we'll look at that next. So this on the left is what you get out of M+. IADL by each item. Those are your factor loadings. They're in logits. So it's the expected change in the logit of per 1 unit change in factor. Now, why am I saying the logit of I'll give you a hint. In the model here, there's where I define my loadings, 1 per item. How many submodels are there per item? There's 3 in this case because there's 4 categories. All the submodels share the same loading. So I could say the same thing 3 different ways, and each way would be correct. For every 1 unit increase in theta, the logit of picking something greater than 0 goes up by 6. For every 1 unit increase in theta, the logit of picking something greater than 1 goes up by 6. Want to try the last one? For every 1 unit increase in theta, the logit of picking something greater than 2 goes up by 6. And that's why I abbreviate by saying the logit of because it doesn't matter which one I put in there. We're assuming it's the same. That assumption is called proportional odds, and it is not something that you can change with this type of model in M+. It's hardwired into this ordinal framework. Yes, sir? The probability of, you mean the probability of each answer? Yes, in the aggregate, marginally it will, but not at any given level of theta. I don't think that's true. I'd have to check on that to be sure. So like in this, like we know that the probability, like if I didn't have a theta and I had the model estimate thresholds, they would perfectly describe the proportion of responses in each category. The proportions that you end up with here would be based on a theta of 0. I don't know that they would hold exactly sum to 1 at any other point. I don't know. I have to check that. So these numbers look huge because they're in logits. But item 7 looks like it's doing the worst. They're all these are on the same scale, so we can eyeball them across that. I have bolded some of the values because I'm using them in calculations below. Let's do the thresholds for item 1. Do you want to do thresholds or intercepts? Anybody care? Intercepts. Okay. Wait. There. Okay. Now it's an intercept. So 9.8 is the predicted logit of answering greater than 0 for someone with a theta of 0 for item 1. What does a logit of 9.8 mean? Anybody? It's really high. It's like a probability that's almost 1. So if you have a theta of 0, odds are pretty darn good that you are going to answer 1 or higher on that item. Next one, the intercept that goes with the second submodel. At a theta of 0, the logit of answering greater than 1, so picking a 2 or a 3, is 6. A logit of 6, still almost 1. Finally, we get to something that's off the ceiling, the third one. At a theta of 0, the logit of picking something greater than 2 is 1.2 at a theta of 0. 70%-ish, maybe, something like that. So all of these things are telling us about what would a theta of 0 look like. What would that kind of person be able to do? Pretty much they're guaranteed to be able to do this item with the highest category. But if you want to know, well, what kind of person would this item be helpful for? That's where we have to translate these intercepts or thresholds into B's. So let me translate each one back into a threshold, because that's what it gives you. So if 9.8 is the logit of an answer of 1, 2, or 3 when theta is 0, negative 9.8 is the logit of a 0 instead of 1, 2, 3. Likewise, 6 is the logit when theta equals 0 of answering 2 or 3. Minus 6 is the logit of answering 0 or 1. Last but not least, 1.2 is the logit of answering 3 when theta is 0. Minus 1.2 is the logit of answering 0, 1, or 2 instead. I hate thresholds, but I want you to know what to do with them. There. Put it back. And I worked out the math for how the models would give you the predicted probabilities down here. So it starts off with the intercept, because it's minus times the threshold, plus the slope times theta. So you can figure out for any theta level what the probability of answering in that threshold would be. Yes, question?
So the 6.846 would increase that value, or would it be also, would it increase the probability of
Increase.
So
Yep.
for a theta of 1, that person would only answer 3.
So this first submodel right here is answering something greater than 0. So if theta were 1, it would be even closer to 1. All 9s out to however many decimals you want to track, right? Yeah, so this one right here is the only one where you could see any movement. And this is the difference between something lower than 3 and 3. So yeah, if they have a theta of 0, then they have a 0.78 probability of answering 3 instead of something lower than 3. At theta of 1, the logit would increase by another 6.8, which would get this probably pretty close to 1. how are we doing? I know this stuff is hard, and I'm sorry. But eventually, if you practice enough, it will get easier. You never know what you know until it just comes out. Can I tell you a story of how I learned about this with my son? Let's see. So, recent picture of him. This is at the Train Diner in Kansas City. I don't know if you guys have been there. It's the most awesome place for children. What is it called properly? What is it? Fritz, yes. No, you order hamburgers and French fries, and like little trains drive around the top of the room, and then they drop your food into a basket at your table. It's the most awesome thing. So yes, this is him at the Train Diner. So his big sister is staying with us this week over her fall break. She's 11. She normally lives in Alabama. And she was playing with him downstairs, and he hit his head on the wall. And he said, "Damn it." And so she whipped out her phone. She's like, "What did you say?" He's like, "I said, damn it." So then we asked him, "Where did you learn damn it, Huey?" And he said, "Well, so Daddy asked me to come back, and I didn't listen. And then he said, 'Damn it, Huey.'" And I was like, "Oh, that sounds entirely probable." And it wasn't my turn to get in trouble because I'm certain I've said much worse. So yeah, I previous to this, I had thought the only way he knew how to express his anger was because that's normally what he does. "I don't want to do that." But no, he's much more sophisticated than I would have thought. Now it's, "Damn it, Mommy, I don't want to wear that shirt. I want to wear the one that was dirty that I wore yesterday." Damn it. So pretty soon, if you work with this enough, even if you didn't think you're learning it, you'll be like, the threshold is the logit of the zero response when a theta equals 0. Damn it. And you'll know. And then you can feel good. It will eventually soak in. But as much as these are not helpful, what you get on the other page is helpful, I would argue. And so this is the code that I gave you to get that. So then you don't have to say, "Damn it, what's the threshold?" You can just ignore that they even came out. So I figured out this new looping thing that M+ introduced 1 or 2 versions ago, which is super nice. This is the equivalent right here of writing 7 lines of code. So since we have 7 items, every parameter that is item specific, I'd have to write the thing out 7 times, and I don't have to do that now. So I am computing A's out of my loadings, where the percent sign, if you're over 30, that is a percent sign. If you're under 30, that's a hashtag, right? Or a pound sign? Pound sign, yeah, not percent sign. That's pound sign. So I computed my loadings, which in this case are the same, I computed my discriminations, my A's, which are the same as the loadings in this case because my factor variance is 1. But this is why I put it in here so that in case I change it, the formula stays the same. Likewise, here's B1, which is the threshold minus the loading times the factor mean. So if the factor mean is 0, that part drops, divided by the loading times the square root of the factor variance. So this part drops if it's 1. So a simplified version of the formula is that a B value is threshold divided by loading. So I'm making it do the math so that it not only gives me the point estimates, but it also gives me standard errors. And here they are. So the discriminations are the same as the loadings. And because I asked for the difficulties in order of threshold rather than item, they're in a different order than the other side of the page, but I've highlighted the ones that would correspond to this. So here, minus 9.8, we said was the threshold. That corresponds to a difficulty value of minus 1.4. So minus 1.4 is the theta value at which you have a 50% probability of answering greater than 0. The next one down that I've highlighted, minus 0.9, that's the theta value at which you have a 50% probability of answering greater than 1. And last but not least, minus 0.18 is the theta value at which you have a probability of 50% of answering 3. So I took those numbers and I threw them into Excel. Let me find where I did that. Distributions, yeah. And I made a picture. So you can see in the spreadsheet, I calculated them to make sure that they're the same, and then I put them in the handout too. So let's look at what the model says then. So here are some examples of category response curves. So this then takes those thresholds, NBs, and rearranges them to give you the predicted probability of each response category at each theta. So the one on the left is the first item. It has an A, or a loading, of 6, so it's nice and steep, whereas item 7 is the worst one. Its A is much smaller. It looks like there's less of a range over which the middle categories get used as a consequence. Here are the item information curves. Note that they look like teeth. They're all jagged. That's because each item contributes in 3 different ways. So the shape of those things is dependent, the location is dependent on where the B values are, the height is dependent on the A. So item 1 was the one that had the loading of 6, that's why it's the tallest. It is centered between about 1.8 and 0, because that's where its B values were. Whereas item 7 is this one down here, the light gray one that's almost flat. Item 7 looks like it's not terribly helpful relative to the others. The sum of these item information curves creates this test information curve, which I then translated into reliability, which looks like this. So if I use 0.8 as a benchmark, my test does a good job at measuring people from about, minus 1.8 standard deviations up to about 0.2 or so, 0.4, I had said, and then it tanks. Because here are my item parameters. So I have discriminations at the top, and I plotted the difficulties at the bottom. So if we look at this, couple of trends. If we look at the overall location, we don't have any items except 7 that are measuring anything less than about 2 standard deviations. So as crappy as 7 looks with respect to its loading, we need it if we want to measure low people. Everything else is concentrated between about -2 and 0. Nothing goes above 0. And that's why our reliability tanks above 0. So we'd have to either find some harder items or find some way of differentiating, adding another category to go up here. So I had made a suggestion here. Instead of just can do it, maybe it's can usually do it or can do it all the time, something like that. Some way of differentiating the highest people. In contrast, look at how close red and yellow are bunched together in most of these items. What does that tell us? Well, there's not much difference in terms of where their B values are. That means that can't do it and big problems doing it are not that different to folks. They're not using them in a way that is helpful. So when you see that consistently across items, that might give you pause for adding or using those categories. It's a common belief that having more category options is always better, but not if people don't know what to do with them. Not if people don't use them the way you intended, then you're just introducing noise. And here's the distribution of the trait. That is a direct consequence of that reliability function. We have nobody past theta of 0 or so because they can't be. We don't know how high those people are. They're all piled up. I also note that the trait variance was supposed to be one but the variance of the estimated factor scores is only 0.8. So they're shrunken. That's why we don't want to use factor scores unless we absolutely have to. The shrinkage tends to go away once you have more items. 7 is probably not enough. The average standard error is 0.3, which is pretty big. If you think about 2 standard deviations around that, being able to characterize each person's data. All right. So, questions, thoughts, comments? Put that up there. So as a sort of summary note, even if you have Likert type data that say have 7 categories and they're perfectly normally distributed and you could have used CFA, for this reason alone, these models can be helpful in evaluating how people are using the categories and whether or not you need more or fewer and whether you'd want to add more to the top end or the bottom end. They also are helpful if you're trying to build any kind of short form, because you want to make sure that you're covering the range of the trait regardless of how good the loadings are. If this particular item is not very useful, it could be because there's not many people who answered the lower categories, or you might just need another item that's low that might somehow work better. But I wouldn't get rid of 7, even though it looks like it's not helping much, because it's helping in an area where no other items are helping. Questions? Yes, sir. These ones? Oh, these ones. Yes. Steep is good, flat is bad. So the steeper it is, generally the more distributed the categories will look. There will be a point on the trait at which each type of answer is most likely, whereas the flatter it gets, the more the ends are going to dominate and the middle starts to go away. So steep is good, flat is bad, generally speaking. This one is centered around this point minus 2.5 standard deviations on theta, whereas this one spreads a lot further. If I have a theta of 2.5, the most likely answer has to be 4 because 4 is the end. But we don't know if there had been a 5, how someone might have answered. So the ends of these look more certain than they actually are because there is no alternative. So that actually works out pretty well. So it looks like we are going to get to our new example potentially on Monday. So what we're going to introduce next is how to introduce not applicable responses into this idea. Because not applicable isn't part of the ordering, but it still might be informative. So we're going to show you how to do that. Any questions before we adjourn? All right, so homework 4 is up. Let me know if you run into problems. Office hours start now.